All right, this video covers a least squares regression line. Now, in previous years, you probably have referred to this as the line of best fit, a line that goes through a scatter plot. Well, in AP statistics, we're going to call this the least squares regression line. We're going to do a whole nother lesson pretty soon here that covers where it actually gets this crazy name, least squares regression line. But for right now, we're just going to really analyze the equation and what it does. All right, so here's the basics. A least squares regression line is just like a line of best fit. It is built to predict a y with a given x. It cannot work in the other order, meaning you cannot take a y and solve backwards for an x value. There's a big difference between a predicted y and an actual y. So here is the equation. And in this equation, we kind of demonstrate the idea that this is to predict a y. So here's the equation of the line of best fit, which we're going to call the least squares regression line, LSRL. Now, over here on the far left, we have y hat. And we literally put this little hat over top of the y to signify that it is a predicted value. This is not an actual y from the graph. It is a predicted y based on our equation. The actual dots in a scatter plot, those are actual. Those are real values. This is just the predicted line. So we do want to make sure we put that hat on it. And it's literally called y hat. Then we have the formula a plus bx. A is the y-intercept, b is the slope, and x is the actual given x value. That's the explanatory variable, the independent variable. So a is our y-intercept. It tells us what happens when x is 0. And the slope tells us how y changes for each change in x. So what the heck can you do with a least squares regression line? Well, there's 4 major things we want to do. 1, we want to make predictions for y with a given x. 2, we want to interpret the y-intercept, a. And next, we want to interpret the slope, b. And then finally, we want to find residuals. Let's go over all 4 of these things one at a time and explain to you how we solve them or how we do work with them. The first is making predictions for y with a given x. It is as easy as taking a given x value and plugging it into the equation. It's actually very, very simple. The only thing is that make sure to call the prediction a prediction, which is why we say y hat. Don't ever plug in an x value and say that this is going to happen. No, this is just what is predicted to happen based on our line. This is not something that is guaranteed. It's, again, just a prediction. So you got to make sure you designate that. Once again, you cannot take y and solve backwards for x. Algebraically, it makes sense. You can plug in a y and solve backwards for x. But statistically, you cannot do it. The idea is that this equation was specifically built to go one direction. You plug in an x and get a predicted y. It cannot work the other way around. Okay, what to watch out for. All right, when you are making predictions, watch out for something called extrapolation. Extrapolation is basically reaching outside of your range. So making a prediction outside of your data range. You can't predict too far into the future or the past. So basically, if your equation was built with x values ranging from 25 to 75, don't make predictions outside that range. Only stay within the range you have. When we look at an example, I'll talk a little bit more about extrapolation. All right, next up is interpreting the y-intercept a. The y-intercept tells us what is predicted for y when x equals 0. So we think about what should y become if x is 0. That's a pretty easy definition of a y-intercept. Due to possible extrapolation, however, this number might not make any sense in context. Meaning for a y-intercept, you're kind of thinking about what y could be if x is 0. Well, if 0 is extrapolation because it's outside of your data range, you might get a value that really doesn't make any sense at all. But it doesn't matter. We still interpret it if we're asked to. All right, next up is interpreting the slope b. The slope tells us how the predicted y variable changes as the x variable increases by 1 unit. So again, the slope is telling us how does the predicted y change for every increase of 1 unit in the x. Make sure to always use the word predicted when referencing the y variable. All right, how to interpret slope is one thing that a lot of kids do kind of find a little bit tricky and they mess up on. So my recommendation is to interpret slope. The first thing to do is take your b value and write it as a fraction. So take that b value and put it over 1. Again, any number, even if it's a decimal, can be made into a fraction if you write it over top of 1. The 1 is always the x variable. Just make sure you remember what its units are. So it's always in 1 unit of x. And then the b is always the y variable. That again is measuring whatever units the y variable is. So it makes sense that the slope tells us that every time the x unit goes up 1, the actual y variable goes up or down b. When I say up or down, it's because it could be a positive or negative. The x variable is always increasing no matter what. It's the b variable, the y variable, right? The b that could go up or could go down. And again, this might seem a little bit fuzzy right now, but once we do an example, it should make complete sense. Now again, how do you actually interpret the slope? Well, I'd say to follow the script. Here's a script. All you got to do is fill in the blanks, and it's actually pretty easy to do. As the x variable increases by 1 unit, the predicted y variable increases or decreases by b units. So when you're actually doing this for a real problem, you're just going to substitute. Instead of writing x variable, you would put context there. What is the x variable? Same thing for y variable. You wouldn't just say y variable. You would actually put the in context, right? The words of what the y variable is. Don't forget the word predicted. It's very important that you put that word there. And then also, how do you know if the b value is going up or going down? Well, you just got to look. Is it positive or is it negative? Positive, it's going up. Negative, it's going down. So it's a pretty easy script to follow when you interpret the when you interpret the slope. All right, next up is finding the residuals. So what the heck is a residual? You've probably heard that term before, but maybe never really knew what it was. Well, a residual value is how far off the predicted y is from the actual y. Remember, our equation is predicting y variables. Somewhere out there is the actual y point, the actual point on our graph, and the distance between them is the residual, okay? So each point on a scatter plot does have its own residual value, and to find a residual value, you take the actual y value minus the predicted y value. So that's y minus y hat. Again, another reason why we need to put that little hat to signify a predicted y. And the way that I remember this formula is that A is the first letter in the alphabet, so A goes first. So actual y first minus predicted, because it's very easy to flip-flop that and you'll get the wrong answer. So because the order of subtraction matters. So make sure you do the actual y value first. All right, a couple of facts about residuals. All of the residuals should add up to 0. This is because some points are above the line and some points are below the line. Just kind of makes sense, right? Some values are going to be over-predicted, some values are going to be under-predicted, and that's why if you add up the residuals, you will get them to cancel out and get a 0. Small residuals show that the line is good at making accurate predictions. Again, if your points are all close to your prediction line, that means that they're pretty close together and that your predictions are fairly close to what actually happened. Positive residuals mean the actual value was above predicted. Negative residuals mean the actual value was below predicted. Residual values should kind of be all over the place, and I'll explain this in 1 second, but you should have positive residuals, you should have negative residuals, you should have big, you should have small. This shows that your line does a nice job going straight through the data. All right, so here's the example that we're going to use today. All right, and this is an example of a scatter plot where we have how many miles are on a truck versus how much does that truck cost. Now notice the red dots are our actual scatter plot, right? And we made this line of best fit, this blue least squares regression line, go through them. And the equation is y hat equals 38257 minus 0.1629x. We'll talk a lot more about that in a second. But the idea is that how far each point, is from the line is a residual. So let's talk about this guy right here, right? This guy, this point, this truck is above predicted. So here was its predicted cost on the blue line. Its distance in between is the residual. So again, the actual value minus the predicted value is the residual. And every point has its own residuals. So you'll see a whole bunch of positive residuals, and then notice you'll see a bunch of negative residuals below the line. And then you're also going to see a nice mix. For example, this is a very small residual. It's very close to predicted. Here's kind of a medium-sized residual, another small residual. Then you're going to have some bigger residuals like these guys. That's a good thing. Your residuals should be mixed because that means that your line is actually going through the points. Just kind of pretend for a second, right? Imagine that this was my line of best fit. Clearly, that blue line does not fit the data. It's not even close to all the points. Every red dot is above it. That's not a very good line of best fit. It doesn't fit the data at all. So again, if a line truly does go through your data nicely, like it should, you should get a nice mix of positive and negative residuals. All right, let's explore this problem a little bit more. Here's the example in words, all right? So everyone knows that cars and trucks lose value the more they are driven. Can we predict the price of a used Ford F-150 Super Crew 4x4 if we know how many miles is on it? A random sample of 16 used F-150s was taken, and here's the data below. So we have all the data, we have the miles of each car, and we have the price of each car. So we can make a scatter plot. So here's a scatter plot of the data. Obviously, miles is the explanatory variable, and the y variable is the price. How much does the miles predict the price? And again, we draw this nice line that goes through the data. Later in the next topic, we will cover how do we know that is the best line. But for right now, you guys get the idea of what's a good line, right? A line that goes through the data. Once again, notice that it does go through the data, meaning that there are points above the line and points below the line, which means that I do have my line of best fit. All right, here's the equation of that line of best fit. And again, in a separate unit, we're going to talk about how to actually create this line, but right now we just want to make sure we understand how to utilize it. So the equation is the price predicted, or y hat, is 38,257 minus 0.1629 times x, which is the miles driven. Now, I wrote this in two ways. This top equation is obviously kind of generic. It just uses x's and y's. A lot of times, kids like to use words in place of x and y that make it kind of like gives the equation some of its own context. So instead of saying y hat, we say price hat. So we put this big hat over top of price, the predicted price. And then instead of x, we actually write in parentheses the x variable, which is miles driven. It kind of just makes it a little bit easier to understand. All right, so we learned about 4 things that we can do. Here's the first. Predict the price of an F-150 truck that has 82,000 miles on it. This is so simple. All you have to do is take your equation, which was y hat, remember that's price hat, equals 38,257 minus 0.1629 times x. But instead of x, again, x is how many miles is on the truck, I'm actually going to plug that in, 82,000. And then all you have to do is solve for it, right? So if I just type this into my calculator, not very difficult, I get a price of $24,899 and 20 cents, I believe. And again, if you don't believe me, just grab your calculator, 38257 minus 0.1629 times 82,000. And again, $24,899.20 comes up. Now, we also talked about extrapolation. So is this a good prediction, or is this extrapolation? Well, look back at my data. Basically, a truck with 82,000 miles on it is within my data. So look, I had some trucks with 70,000, some trucks with as high as 130,000. I even had one here as low as 4,000. So as long as I'm making a prediction on a number of miles that was actually involved in my data. Again, my data ranges from, looks like it ranges from as low as 4,000 miles to as high as 144,000. So as long as I'm making predictions within that range, I'm good to go. Extrapolation would be if I try to predict a truck with 10 miles. Well, no trucks that I used in my scatter plot had only 10 miles. Likewise, I would never want to make a prediction about 200,000 miles because none of the data that I was using involved any mileage that high. So stay within your data. That is what we mean by not having extrapolation. Okay, so that's pretty easy. It's just a matter of plugging in a value. But remember, like I said, at no point can you take the price of a car and back solve for how many miles. You just can't do it. Algebraically, you could, but statistically, we would say that's not what this equation is meant for. All right, let's go ahead and interpret the y-intercept of 38257. Remember, y-intercept is what happens when x is 0. So I'm going to follow the script here. When a truck has 0 miles, again, that's the x value, right? And then a y-intercept is what happens when x is 0. The predicted price is $38,257. Now, I did what I was supposed to. I interpreted it in context. I talked about the truck was 0 miles. That's all context. The predicted price of the truck is $38,257. However, this could be extrapolation, again, because I'm trying to make a prediction on 0 miles. None of the trucks I looked at were quite that low. So again, this could be extrapolation. It doesn't mean that this is wrong. It just is, I just have to kind of consider that. But it also kind of does make sense that a brand new truck would have 0 miles. So a brand new truck would cost somewhere around 38,000 miles, again, $38,000 predicted. Okay, so that's really how simple it is to interpret a y-intercept. Just make sure you do it in context. Okay, next up is interpreting the slope. All right, so the slope was 0.1629. This is the number that's next to the x, right, in the equation. So here's my recommendation for how to do this. Like I said, I like to turn it into an equation. And you can turn even a decimal into a function. I'm sorry, I'm really messing this up. I like to turn it into a fraction. And you could turn any number, even a decimal, into a fraction by putting it over 1. Remember, the 1 is always the x, which for us is miles. And the top number, the actual slope value, is always the y, which for us is in dollars. So what this tells me, again, I'm going to follow my script, right? The script that I kind of gave up here. Let me just kind of go back to it real quick so everybody sees it. As the x variable increases by 1 unit, the predicted y variable increases or decreases by b units. So now I'm going to come back down here and let's actually do that, right? So here I go. As the miles on a truck increase by 1 mile, don't forget units, the predicted, don't forget that word predicted, it's really important in your answer here, the predicted cost, again this is the y variable, cost, will decrease. Again, how did I know? I want to go back and show you how I knew it was decreasing, because the slope is negative. There is a minus in front of that value, so please make sure you realize that. Actually, I should have even had a minus sign right here on that value. The predicted cost will decrease by 0.1629. Again, that's going to be dollars, right? And you could even round that for the sake of just saying it so that it makes sense to 16 cents. Basically, what we're trying to say is as the miles on a truck increase by 1 mile, the predicted cost will decrease by 16 cents. And again, notice I just followed my script. As the x variable goes up 1 unit, the predicted y variable decreases in this case because it's negative by blank units. And again, the units for me is just dollars here. So as the miles on a truck increase by 1 mile, the predicted cost will decrease by 16 cents. So every time a truck has an extra mile on it, it's predicted that the cost of that truck will go down by 16 cents. So it actually makes a lot of sense in this problem. All right, the last thing I told you were going to have to do is understand residuals. So one actual point on that scatter plot was 68474. That's the x. Remember, x is miles. So that's going to be in miles. And the price was $33,961. That's dollars. So again, this was an actual truck, meaning that a truck with 68,474 miles on it, sorry for the typo there, shouldn't be milers, cost $33,961. What is the residual value for this truck? Well, remember, a residual value is the actual value, the actual y minus the predicted y. Okay? Now, I already know the actual y. I already know the actual cost of this truck is $33,961. What I have to figure out is what the predicted y is. And again, that's y hat. And that's where the equation comes in handy. We have this equation, y hat equals 38257 minus 0.1629 times x. And again, what's the x? Well, that is what I already know. That's the miles, right? So I'm going to plug the miles into the equation, and this is going to get what the line predicted for this truck. So if I plug that in, I get a y hat, a predicted value of $27,102.59. So again, the actual y was given to me in the point, or from the actual data, and the predicted y was found by using the equation. All I had to do was plug in the x value. So the actual price of this truck was $33,961. The predicted price was $27,102.59. Subtract them to get your residual, and if you subtract them, you get a residual value of 6858.41. And that is going to be in dollars. All right. So what does that tell me? That tells me that the actual price of this truck was $6,858.41 over what I predicted. So my line predicted about a $27,000 price. The actual was about almost $34,000, and that's where we get this $6,800 difference. So the residual, again, is the difference between the actual value and the predicted. And we can actually try to find this value on our scatter plot. So remember, 68,000 would have been somewhere right around here. So it's probably this truck right here. Okay, This truck right here is probably the one we're talking about. Again, I'm just kind of estimating based on the price, right? It had about 68,000 miles and cost about $33,000. And we noticed that that truck, again, was $6,000 over what was predicted. Because here's what was predicted, about $27,000, and here was the actual. So the residual, again, is the difference in between them. All right, guys, so that's it for this video. Hopefully you understand the 4 things you need to do with a regression line or a line of best fit. You got to be able to make predictions with it, which is really basic. Interpret the y-intercept, interpret the slope, and calculate residuals. You'll get a lot of chance to practice this in class, and hopefully you found that very easy.